All right, up next, electric potential and electric potential difference. There's a real danger of things starting to all sound the same in this unit. All right, there's reasons for this that I'll go over. Please pay really close attention to the concepts we're talking about and what things really are, rather than just thinking of it as names that don't mean anything to you and letters that don't mean anything to you. Okay, it's a nightmare if you just think of it like that. If you pay close attention to what we're talking about, it makes it a lot easier to follow the concepts of what you need to do to make, to do the calculations required for things. All right. So the first thing to know, electric potential. Well, we've already been talking about electric potential energy. What is this so-called electric potential? And I'm doing air quotes, even though you can't see them. So electric potential, this V, is the electric potential energy per unit charge. That's the only difference. Is it's energy per unit charge. All right. It's really is nothing different. It's just sounds different, it's used different, and so on. But you'll see how it gets used as we go through this. Okay, it's unfamiliar to us, right? I think I've said this before. Yeah, like maybe not. I don't know. Anyways, again or whatever. If this was commonly talked about with gravity, it would be a lot more intuitive for us, right? If we talked about gravitational potential energy per kilogram, right? Which we don't. We just don't talk about it that way. So think of a mass at a certain height, you can intuitively think of how much energy it has, and like by thinking of just picturing how much it would hurt if it fell on your foot, right? But that's the amount of energy for a specific amount of mass. If you go to other planets with different gravitational field strengths, that amount of energy would change, of course, right? And so the amount of energy, gravitational potentially energy per kilogram, would then be of interest, right? If you were to look up the gravitational potential in quotes, right, for a new planet that you're going to, you'd have a good idea what to expect regarding the energies of all objects at heights. You wouldn't, not just for a particular mass, right? So that's the issue, right? We don't just hop from planet to planet, but we do deal with situations with different voltages all the time, and so we want to know this electric potential as a new concept because it really gives us an idea of what we're dealing with, right? Electric potential difference is actually what you already have studied and looked at, either just in my review of 3U, or you've seen it in grade 9 science, if you remember that. And you look at and in grade 11, of course, physics. But if you look at like a 9-volt battery, that's what we're talking about. 9 volts. It's the electric potential difference. Okay, they're both measured in volts, of course. But one is the difference in the electric potential, and the other one's the electric potential. So it's like meters or a change in the amount of meters. Like it's going to be the same units. So again, if we talk true again this time, right? If we talked about this with gravity, it would make more sense, right? So this would be the difference in the amount of gravitational potential energy per kilogram between two locations. Okay, so picture items on a shelf, right? Moving a 1 kilogram mass from one shelf to another. How much work would be done to do this? Well, that would depend on your gravitational potential, right? And that amount of energy would be your gravitational potential difference. Okay, I should circle that. So think about how much work would be done to do this, right? That would be equal to your gravitational potential difference. Okay, so hopefully that gives you a good feel for what we're actually talking about here, rather than it just being sort of mysterious electricity concepts. Okay, so again, repeat warning here, but we know electric potential is your electric potential energy per unit charge. And so really we should be expecting like joules per coulomb, right? Well, we call that volts. Okay. So that's your symbol for this. Electric potential is volts. So yeah, it's not really that much more complicated than basic potential energy or electric potential energy, I should have said there. But we only see this with electricity. We only talk about energy per charge, right? So this is a little bit of a repeat about the gravity stuff, right? So yeah, there it is. Since electric potential energy is stored due to work that needs to be done against the electric force to move a charge from from infinity to a particular location, as we talked about in the previous lesson. You can think of, having a charge, this test charge, right? And all that work that needs to bring it there, that's going to be your electric potential, right? So it's how much energy it took to get that one coulomb of charge there, right? That test charge there. So electric potential energy per unit charge, or simply electric potential, right? That's what we call it, is then the amount of work needed, right, to move one coulomb test charge from infinity to some point, and that infinity is your zero energy position, right, to that spot. So if you're moving it in and you're pushing on it to make it go there, that's positive energy. If you're holding back because it's trying to attract on its own there, you end up with a negative energy, as we've seen. And so electric potential V is electric potential energy per unit of positive charge, and so it's 1 joule per coulomb, and of course the usual plus and minus for repulsion and attraction. So you should recall, hopefully, that the term voltage was used in electric circuits, as I mentioned, and it was for the change in electric potential energy per charge between 2 points in a circuit. So we've actually already talked about that one, right? That's your electric potential difference, right? With the new electric potential, the difference part is still part of the concept. It's just a difference in comparison to infinity. So they're not even that different, except you're just looking at potential difference. You're looking at between this 2 centimeter mark and that 10 centimeter mark, whereas electric potential is the entire difference all the way to an infinite distance away where there's zero energy. I think it's just interesting that they're not actually that different from one another. It's just, if you're at an infinite different distance away, it's zero, and so it's just your electric potential rather than your change, right? Rather than your difference. This is just like we've seen before. I'm going to do the height example soon here too, but think of if you had zero money and you gained $20, the difference is $20, right? If you had $0 and you gained, so if you had zero and you gained 20, your actual amount's 20 and your change is 20. But if you had other money, right, then the change wouldn't be the same as your actual amount, right? And we saw this before with gravity too, right? If you think of this as your height, then this is just 20 joules of energy because of your height. If it's a change in height, then it's your change in your energy, right? So it's all kind of the same thing. Your energy, e.g., your gravitational potential energy per mass, is, of course, like we said, that same concept as electric potential. We just don't refer to gravity, right? So since we don't, with gravity, because we don't hop from planet to planet, we don't need to know the gravitational field, gravitational potential as much. It's not as necessary. We do, though, experience different electric field strengths regularly. Whenever we're working with electricity and charges and so on, all these things we're talking about, right? You have 2 charges near each other. What's the electric potential energy, and what's the electric potential, and what's the everything, what their forces, all that stuff. So this concept is useful and studied and talked about, right? So just to recap here, electric potential energy is KQ over R. If we want to do electric potential energy per charge, then that's electric potential, right? So KQ over R, the Q's cancel out. So the Q would be like the spot where you are, and you're looking at another charge, big Q in this case, right? So electric potential is just KQ over R, and then the gravity mass version of things, right, would be your GMM over R, and then it's just like, okay, per mass. So if you have a brick, let's say, the brick is the green M that we're canceling out, right? The capital M would be the Earth. So this is gravitational potential at any spot, a certain distance at any spot. So this distance here from Earth. All right, so let's do it. This is still a little bit of preamble here, I think, but yeah. So we have this potential, right? Electric potential is electric potential energy per charge, and repeat hazard here, of course, right? KQ over R, and so that test charge is canceling out, and so it's KQ over R like we had, right? So again, we have plus or minuses, but it's not a vector truly. It's just pluses and minuses combine logically like integers do. So yeah, so you have these versions of this, right? You have the main concept of being electric potential being electric potential energy per charge, then you could think of it as, this resulting equation of kq over r. Okay, so both of those should make perfect sense, and they're just different versions depending on what numbers you're working with, right? And this is just about the test charge thing being like the one that's feeling the effects of a charge that is creating the field that we're talking about, right? The one that we're, in this case, be a case of a brick relative to Earth. The brick's not affecting the gravitational field to any extent. So a test charge or a charge near some charge that's creating an electric field, you think of it as the charge that's creating an electric field as, really what's causing the electric field, and you're just looking at, the electric potential energy at a spot due to that other one. Okay. All right, so what this looks like, right? So it says, what is the electric potential? A distance of 0.90 meters from a charge of -3 times 10 to the -4. So we want to look at what the electric potential is at that spot. And so obviously we're given these things, right? You're given the charge, you're given the distance away. Excuse me. This charge here, the -3, is the one that's making the electric field, of course, right? So we want the electric potential. I almost said voltage. It's units of voltage, right? But so V is electric potential. Pardon me. In this question, we're told the value of the charge creating electric field, and therefore, we're going to have the kq over r version, right? We have the charge value, we have the distance away, we're using that version. If we were told the amount of energy, if we were told the electric potential energy that it has, then you'd be doing that divided by the charge, right? So we're working with the version we have, the numbers we have, right? Go back to this. We're given this kind of information, so we're using it. If we're given the amount of electric potential energy that a known charge has, we would just be dividing those out, and you'll see that later in this lesson. All right, so so paraphrasing here, we've got this -3.0 times 10 to the -6 electric potential, right? And if you notice, that's a negative number, so that's an attraction situation, right? So energy was released as it attracted to that spot from infinity. So this not bad here. Bad in a lot of ways. How much I want to fix there. Anyways, the electric potential energy per unit charge is negative. In other words, this a 1 coulomb of charge would have -3 million joules of energy at this position compared to a value of 0. As it was coming in, it lost that energy, right? It transformed to kinetic energy and all that, like I've said, right? So I think I want to do one more delete there. There we go. In comparison, a positive charge would have had work done on you to push to get it to go there, right? To against that repulsion. So it would have positive energy at that spot. In your own words, I'm going to leave this one. This is just describe, but I mean, in your own words, describe what's meant by electrical potential. Well, it's what we've just been talking about, right? So hopefully, you have some kind of words that be like those, right? I'm going to move on to this example here. So electric potential difference, right? So that's just a difference in the electric potential energy per charge, right? Electric potential energy per charge, or I could have just said electric potential, as I did. So it's a difference in the electric potential between two locations, same as saying electric potential energy per charge, right? You wouldn't want to focus in your timing of your what you're saying on electric potential energy, right? Because that's not what we're doing. It's electric potential or electric potential energy per charge, right? So all kind of related, but just trying to keep it clear here. So if it requires work to move a test charge from one point to another within an electric field, that amount of work is equal to the difference in electric potentials at the 2 points. It's referred to as the electric potential difference, as we've been saying. So you're moving an object from one spot to another. Note that they always show it like a little curvy path, and what that's about is that the path taken doesn't matter. It's a conservative force situation. It's called. Essentially, the amount of energy you get doesn't matter how you went. It's not like there's no friction dragging along the way as you go. Okay, that's what that's really about. So electric potential difference is the amount of work done per unit charge, right? To move a positive charge, right? We're looking at from one point to another in the presence of an electric field. And so we're looking at delta V, right? So that's really a delta E. So we're talking about this change, right? So we know that, yeah, and again, there's positives and negatives and so on, right? But yeah, so delta, of course, is final minus initial. So really, you can look at this as delta V equals delta EE over Q, right? Delta V, change in electric potential energy per coulomb. Well, there it is, electric potential energy per coulomb. They're both just changes, right? So, potential final minus, the final potential minus the initial potential would equal the final electric potential energy per charge. Take away the initial electric potential energy per charge. So again, both are differences in the amount of electric potential energy per charge. That's why they're both voltages, of course, right? And so here, difference relative to zero at infinity for electric potential means the total amount of energy per charge, right? So you're talking about electric potential. This is your total. If you're comparing to infinity, that's your total amount of electric potential energy per charge. Versus if you're just looking at between two locations, that would just be the change in electric potential energy per charge. Trying to clarify again, right? So here is an example for us to go through. The way they have this worded is kind of strange. So I'm leaving it that way just so you can see that you're going to have to sort of be able to interpret things. And so what we're going to do is we're going to do A and B. We're going to jump right to D because it just makes sense to do that. Just pause for a sec here. All right, I did some aggressive throat clearing, so hopefully my voice stays intact from now on. Doesn't seem like it's going to, though. All right, so what is the electric potential at a position of 50 centimeters from a charge of 2.5 times 10 to the negative 6? Right, and then it says, what's the electric potential at a position 10 centimeters away from that same charge? So this is the potential, this is the difference between the amount of energy at the charge in comparison to zero at infinity, right? So both of these are in comparison to zero at infinity. We're just getting the electric potential at those spots. When we go to get the potential difference between the two, we can just subtract them, right? So it's crazy that they do this part C in between. I'm just going to go ahead and do it in a logical way here, right? So we're going to do part A. We're just going to get the potential at that spot. So we just electric potential energy per charge, right? So it's just going to be the KQ over R, or you could have done it as KQQ over R per Q, right? But the per Q is getting canceled out, right? So it's just a potential at this spot. Like there isn't a Q here, right? There isn't a Q said. That's why that's the 1 coulomb test charge kind of thing, right? Yeah. So if we had a Q there, that's what this next part is, right? This Q value of -2. Well, you'd have to say, okay, well, it's the electric potential energy divided by 2. It's kind of weird to include the 2 and then just divide it out. But you'll see that when we do part C. Okay. So for electric potential, oops, wrong page. For electric potential, you would just have your KQ over R, and yeah, you just get your number. So it'd be like, oh, there's 4.5 times 10 to the 4 joules per coulomb of potential there, of electric potential, right? Same for the other spot, giving you a 2.25 times 10 to the 5. They're a little fast and loose with their significant digits here, so they're going to use 2.25 in the next slide from the ministry stuff. Really, it probably should have been 2.3 to 2 significant digits. Although, actually, no, I'm wrong because of the even rounding rule. So that would actually be 2.2. There you go. So then, well, it would be 2. I should say actually that would be 2.2, not 2.3 for the even rounding rule. But they use actually the 2.25. So they jump back and forth between numbers of significant digits unless there's keeping it till the end, I guess. So I'm in favor of that anyways. So long story short, let's get there. So we got the 4.5 and the 2.25, and yeah, so part D would be just what's the difference between those, right? Part D is just what's the electric potential difference. So you would just find the difference between them. So it would be the subtraction of the two things, right? It's just final minus initial. So we have our 2.25, take away that 4.5, and it gives you a 1.8. And this one here, I'm looking at this being a positive. I'm just not sure about signs on this right now, because I think obviously that looks like it should be oh no, it is a positive. It's just the it's the 10 to the powers that were messing me up, right? So yeah, it is a positive value. I just was looking at the 2.25 and the 4.5, I think it should be negative, and that would happen to you too, I'm sure. So just be careful there, right? This is actually like 22.5, if you will, in comparison to a 4.5. They're both powers of 4. So we're getting a correct positive value. So you can see that this is an attractive situation, I guess, right? Or positive work was done, at least. We're pushing against forces to make that happen, right? Potential was increased since it was pushed. Yeah. So hopefully that makes sense. Yeah. Let's go back to it. We have this thing. We're going from 50 to here. Positive test charge had to get pushed towards there. So positive work was done. It has more energy now than it was. It's a repulsive situation, and so on. All those things, right? Part C is for a specific amount of charge at that spot. It's a little weird to do that at this point, but let's go through it. So this all got jumbled on me for some reason. Notebook likes to do that once in a while. So to find the actual amount of work needed to go from one spot to another, we can just analyze it out, right? So it'd be like, oh well, the difference in the electric potential, like the electric potential difference per charge, would be the work done per charge. And then they say here, since the work done is the same as that change in energy, we can get that change in energy from the potential electric potential difference concepts, right? And so they rearrange this thing and say, okay, we want the charge times that potential electric potential difference. You can basically, you've got how much charge and you have how much energy per charge there is as a difference. So charge times how much energy per charge gives you the amount of energy, right? Hopefully that's making sense to you. And so you have your final minus initial again here. There we go. So I want to point out that amount, right, based on what we did, is known to be 1.8 times 10 to the 5. So this is why the potential electric potential difference concept helps, right? You would just be like, boom, just multiply out and you'll get your number. You get your 360. So you'd have your 1.8 times 10 to the 5 times your Q value of, because this number here is the one that's known. Just circle in purple here. This is the one that's known to be the 1.8 times 10 to the 5, right? So you can just put that in, multiply it by the 2 point whatever number this one is, and you'd get your value. That's 360. Right? Because it was like 2.0 times 10 to the whatever, right? So it all works out to be the same as that in the end. But it's just a long way of getting there if you're doing it for a specific charge for some reason and not taking advantage of the fact that you already know this electric potential difference, right? So yeah, it's 360 joules, right? So if you did it, well, I guess it's just kind of weird to have this again here and then again in part D is why I thought that was kind of weird they did that way. I want to point out that you could, of course, just calculate the electric potential energy that there is at each spot and, subtract them, right? So you'd have electric potential energy at one spot, and then you'd have the electric potential energy just based on the old equation, right? Q over R. And you just, get each of the energies and subtract it all out and get your 360, right? It just would be a lot more calculations, a lot more numbers that you don't need to have because you could take advantage of this electric potential and electric potential difference concept, right? Yeah, the negative value here reminds us this would happen naturally, right? If you let go, this would just happen on its own, right? So, yeah, it's a repulsive situation, or an attractive situation, sorry. depending on which way we're going, right? It's a little bit unclear here. This next slide's about, or this one here, I guess. It's not clear which way things were. It could have been this way as well, right? Where it was going from the 10, initial, going from the 10 to the 50, the way it was worded. So obviously I would just try to have that worded more clearly, or you could ask like, okay, are we going from the 10 to the 50 or 50 to the 10? Yeah. So after completing part C, you'd have this 360 joules thing, right? Remember the other version of the energy equation or potential equation? Where was it? Up here. Go to where we had that version where we'd say, okay, we could do it based on energy, or we could do it based on charge. I have to find where that was now. That one. There we go. So you could think of electric potential as the electric potential energy per charge, or as the resulting kQ over R. Well, now we have that 360, right? So we could say, oh, it's 360 joules per, per charge. And so we could confirm that everything makes sense and look at it that way right here. Right? We could say, oh, there's our 360 per charge. There's that 1.8 times 10 to the 5 again, right? Our electric potential difference that we already calculated in a more logical way, right? It's kind of silly to do this. You'd include the 2 to get the 360, but then you just be canceling that 2 out. So, but it's all true. It's just, why would you, right? In the next question down here, I don't need that slide anymore. I moved it over and forgot to delete it. So in the next question, just look at this kind of diagram here. You've got your electric field, and you've got this motion and so on. And keep in mind that this direction here is the direction a positive would go, right? And so it says if the charge in the diagram is a negative. So if this is a negative charge right here, what would happen? What would it be like moving it from there to there? Okay, so if it's a negative charge, is the work done to move the charge from A to B positive or negative? Okay, so if it's a negative, like a positive would naturally go this way, right? A negative, you'd have to push on it to make it go that way. And so that would be positive work you'd be doing, right? Is the electric potential energy higher at point A or point B then? Well, we're adding energy as we're going, so it's going to be higher at B, right? Yeah, a smaller negative number, I guess, right? Is that right? We have a negative here. You'd have to think about where you're attracting to or from, I guess, for that. Is electric potential greatest at point A or point B? Well, electric potential is just potential energy per charge, right? So if this one's the greatest, then clearly this one's going to be the greatest. It's just per charge now, right? So it's just now the smaller negative number per charge rather than just being the smaller negative number. Right, closer to 0 at infinity if you pushed all the way to there. Will the electric potential difference due to this motion be positive or negative? Well, it's going to be positive, of course, because you're doing work, positive energy on the system, right? You have a small negative number at the end, take away a larger negative number you started with, and so on. It's this, I don't know if I have the graph handy or not. It's the graph where you've got this negative line underneath, right? Whoa. That. What if it was a positive charge? Well, if it was a positive charge, it would go that way on its own, right? And so it'd be negative work done. Okay, so it would be trying to go that way. You'd be actually holding to the left as it travels to the right. And so you'd have a negative force times the distance. Electric potential energy then, higher at one point than the other, would be higher at the first one, right? And at the A. The energy per charge would be at A as well. And the electric potential difference would be negative in that case, right? Because you would have allowed it to let energy out. So energy out per coulomb would also be out, would also be a negative. So that is that. Like I said, you might need to watch this one again. Just the V and the delta, like the electric potential difference, and the distinction between that and electric potential energy. It all kind of sounds the same, right? So you really have to try to nail down those things. And honestly, I'm in that same boat. Like, it took me a while to put this lesson together because I have to really, really focus to make sure I'm talking about the right stuff. And I hope I said the right things each time. This lesson, I think I did. I don't, yeah. maybe if I listened back through, I'd be like, oh crap, I said electric potential energy instead of electric potential or something. But I'm pretty sure I was careful enough. I hope. Forgive me if I made a mistake, but I'm a human. So there you go. Yeah, thanks for watching.